вечора, українські радіаційні онкологи, медичні фізики. Слава Україні! Дуже дякуємо, що приєдналися до Research Methodology Course for Ukraine, Help Ukraine Group, Astra International Research and Development Committee. We are all excited to present Lecture 9 in the course, and our topic today is Statistics in Clinical Research 2. And I'm super excited to welcome two amazing educators and podcast hosts as well. Dr. Kristin Sainani and Regina Nuzzo. They gave an amazing lecture, if you remember, last month on basic statistics, on descriptive statistics, p-value. Today they will talk about more advanced statistics for continuous discrete variable and survival outcomes in trials. So we are honored to host them. Let's talk a little bit about their bio. Dr. Kristin Sainani is professor at Stanford University. She's internationally recognized science journalist and educator. She teaches the widely used Coursera course, Writing in the Sciences, and leads Stanford Online Medical Statistics Certificate Program. Dr. Sainani works as a statistician in sports medicine and serves on the editorial boards of several major journals, including Medicine and Science, Sports and Exercise, Sports Medicine, and American Journal of Sports Medicine. She's written extensively about health science statistics for both academic and general audiences. And she's also the co-host of the New Normal Curves podcast that I started listening to since our last lecture. And Dr. Regina Nuzzo is an award-winning science journalist, professor at Gallaudet University, who specializes in communicating statistics with clarity and creativity. Her work has appeared in Nature, the New York Times, Scientific American, New Scientist, Science News, and other major outlets. Her feature article on p-values in Nature received American Statistics Association Excellent Statistical Reporting Award. Dr. Nuzzo has written for the Proceedings of the National Academy of Sciences and for the American Statistical Association, and she served as the statistics educator at Stanford University as well, where she co-teaches the graduate course, Clinical Informatics Management. She's also the co-host of the New Normal Curves podcast. I would highly recommend this podcast. It's quite amazing. So we are very happy to welcome both of you to this second lecture in statistics in clinical research. So we're very eager to listen to what you have to share today, and the podium is yours. I'll stop sharing.
Thank you, Natalia.
Thank you. Go ahead and start us, Kristin, while I get us set up.
Okay, yeah. So Regina is just going to project the lecture slides. But what we're going to be talking about today is actually, we talked about foundational concepts last time, p-values, confidence intervals. Today we're going to talk about what statistical tests are appropriate for different data situations and how to decide, and some of the assumptions behind those models and how to interpret them. As Natalia mentioned, we have a podcast that we've now done a full season on. We have 23 episodes, which we're quite proud of, called Normal Curves. And we do have an episode on p-values, which follows up nicely to the last lecture. But the one I'm showing here, we have a few that deal with cancer, but the exercise in cancer episode, the example that we're going to use in the second half of this lecture actually is on a recent randomized controlled trial on exercise after colon cancers. We talked about that study in one of our podcast episodes. So I'm going to use it as an example here because it's a really interesting study.
So as Kristin mentioned, today we're talking about common statistical tests. First, we'll be going through an overview and how to figure out what kind of statistical test, and then talking about statistical tests for three particular types of outcomes: continuous outcomes, discrete outcomes, and survival outcomes. And these are the most common ones that we'll see. So let's start with the overview of statistical tests. This is just a very handy chart. Do you want to go through it, Kristin? Go ahead.
Oh, no, you go. You take it.
Okay, this is just a very handy statistical chart to help get you oriented. Common statistical tests. Let me just lead you through what we're doing, what these colored things are. First, you want to ask, what is the outcome? What is the dependent variable? What is the thing that we're most interested in explaining. And we have continuous, binary, count, time to event. We'll be talking about all of those today. Then the important question that is often skipped, are these observations that we have, are they independent or are they dependent? Are they correlated? And we'll talk about what we mean about that. And lastly, we want to ask whether the assumptions for each model, each statistical test are met. And if they're not met, then we have to look to some alternatives.
All right, so I'm going to talk a little bit about this concept of, are my observations dependent, correlated? We use lots of different words for them in statistics. I want to make sure we're all on the same page about what we mean by that. And we actually talk about correlated observations in one of the episodes in Normal Curves, the pheromones episode. So if you want to hear our kind of fun explanation of it, that would be the episode to go to. So, but we always start by asking, what is it I'm measuring? And that's really a key question. And sometimes you have a choice. So what is the unit of observation? Often we are just measuring a person, right? That's the common one that most studies measure, but it doesn't always have to just be a person. So I do a lot of statistical review for physical medicine and rehabilitation. And so sometimes they're looking at a limb, like the right hand or the left hand, your right knee or your left knee. And sometimes in dermatology, they'll put cream on one side of the face and placebo on the other side. So that might be half a face. So if you are measuring the outcome on a single limb or a single half of the face, then if you've measured two halves of the face or two limbs from the same person, then you have correlated observations. They belong to the same person, meaning they're more likely to be alike. And actually, I think in the pheromones episode, Regina, it was armpits. People have two armpits. That was the correlation for the pheromones. So that's the first question to answer. What is that unit of observation? And then if you know that, then you can ask the question, are those observations independent or are they correlated? You need to know the unit of observation first. And again, you might change that. So if you decide you were measuring limbs, but you don't want to have to account for the right limb separately from the left limb, you might average over the limbs. You have to make that decision. Independent observations are unrelated, usually just different unrelated people. Again, that's the most common. But what if you have the same person over time? If you measure the same person at different time points, we call that repeated measures, and that person is going to be more similar to themselves at different time points than they are to other people. So that's an example of correlated observations. And again, two legs from the same person, two knees from the same person, and so on.
This shows you a little bit of what correlated observations would look like if you get your data in like a spreadsheet sort of format. And we'll talk about why it's important in a moment, but this is just to help you see. So this first column has the participant ID. Let's say we have, person number 1, 2, 3, 4, and 5. We can see that we have multiple rows for the same participant. That means they belong to the same person. That means they are correlated. So that's your giveaway right there. Even if you're not coming to it conceptually, if you're looking at it from a spreadsheet, this is what it looks like.
Yeah, and I think people get confused. I often get the question like, oh, well, I've got height and weight in the data set, and those are correlated. But those are correlated variables, right? So if you've got two columns that are related, those are correlated variables. So we're talking about, rows that are related, not columns, if that's helpful. Yeah. So what happens if I ignore my correlations? Why do we care about this? So it turns out you will get your p-values wrong. You will get looking at the differences between people or clusters. So if I have two different, I have two different groups, but I've measured multiple limbs. So let's say I have a group of people that was treated with a drug and a group of people treated with a placebo. And on the people measured with the drug, who were treated with the drug, I measure their right knee and their left knee. But I count that as if it's two separate knees from two different people. I will have overcounted essentially. So if I'm looking at treatment versus placebo, so the legs that belong to the same person are, in the treatment group or the placebo group, I will end up overestimating my statistical significance. My sample size will be artificially high. And So, because it's like you're over counting. You're counting somebody's knee twice when it's really just one piece of information. Now, there's the other situation is if you've got if you treat one side of somebody's face with a placebo cream and the other side with a treatment cream, and you want to compare within that person. If you ignore the fact that those two sides of the face belong to the same person, there's a whole bunch of variability that you can explain by which person the sides of the face belong to. And so you end up in that situation overestimating the variance, and your p-values will actually be too high. You could miss out on statistical significance. So it can go either way, but your p-values and your inferences will be wrong.
That is why we care so much about it. Now, ready for our pop quiz. Remember, we have 5 of these. There are 4 different scenarios here. In which of these are the observations most likely to be correlated, that is not independent? And we have it in poll. While you're looking through it, I'll just read through the different examples. Situation A, you're taking one tumor measurement from each of 100 unrelated patients that are getting radiation therapy. B is you're measuring tumor size in the left and right lungs of the same person. Situation C, tumor volume is recorded once per patient, and the patients are randomly sampled from multiple hospitals. Or D, a single performance score for each patient is recorded at their time of enrollment. So which of these has correlated observations? Whoops. Sorry about that. Well, everyone's going to get it right now. I'm gonna move my my very sensitive mouse over there.
That's okay. We're almost there. So waiting for a little bit more answers. So yeah, 80%. Yeah. I'm ending the poll, sharing results. So majority, 42% said A. And
okay.
only 17% said B.
B, okay, which we saw from my slip was actually the correct answer.
Regina.
Okay, so let's talk through what this is and why. Let's talk about why B is the right answer, first of all. So remember we were talking about correlated. Kristin talked about, okay, you have, left leg and right leg, or left half of your face and right half of your face. These are dependent. They're correlated because they're within the same person. Now, a lot of you said A, one tumor measurement from each of 100 related patients. So this is the classic independent, where this is what we have typically. We're just recruiting people for a clinical trial, and we have 100 people. We're only measuring one thing per person, and they're all independent and unrelated. So we'll save time for questions at the end. So if this one is confusing, you can go ahead and ask this. But correlated dependent observations are a very tricky concept. So if you didn't get this right, that's okay, but be sure you understand it. You want to take the next bit, Kristin? I don't know if Kristin.
Yep. Sorry, it's just my internet's been a little finicky, so I just wanted to make sure it's working. Okay, so we are now going to talk about, that's your overview for how you choose the right statistical test, but now we want to zero in on when your outcome, your variable is a continuous outcome. So, things like a number. So continuous outcomes would be things like, a score on a pain scale, or a score on a cognitive function scale, or BMI, or weight, something like that. So again, we have a continuous outcome. We are choosing things based on whether we have independent or correlated observations. So we're going to start by talking about the test for independent observations, which is t-test, ANOVA, correlation coefficient, and linear regression.
Okay, so here is the secret that many people don't tell you in statistics class, and that is all of these are actually equivalent. They are the same statistical test, just dressed up in different clothing and different names. And if you want to go on and get an advanced degree in statistics, you too can learn how to mathematically prove that they are all the same. But we're going to give you a little bit of an example here. There's various historical reasons and mathematical reasons why we give them different names, but just know that it's the same, meat and bones underneath. Now, we already saw a t-test, if you remember from our lecture last month. We had 10 people, 20 people total, 10 enrolled in a control group and 10 in a treatment group. And the outcome is tumor size. And this was our box plot, remember, we wanted to see whether the treatment actually is better than control. So we go through this list of questions that we're talking about. What is the outcome variable? Tumor size. Is this quantitative? Is this continuous? And yes, it is. The answer is because we are looking at tumor size in millimeters, which is a number, right? So we're not just saying, is it bigger or smaller? That would be binary. We talk about those things later. It's continuous. Are they correlated? They're not, because we just have 10 independent people in control in treatment groups. We need to ask how many groups are being compared. And well, here, are there groups being compared? Yes, there are. There are 2 of them in here. And this is helping us narrow down to a t-test versus an ANOVA or something. The last very important question, are the assumptions for the t-test, for these t-test, ANOVA, linear regression, are the assumptions met? And the assumptions are normality and homogeneity of variances. And that last term is just a fancy term for, do they have similar spread? And we want to see whether those assumptions are met. And it's really hard to tell from the box plot. The box plot is great, but what we want to do is go in and look at those histograms.
Yeah, so these histograms, if again, we look at these, we're saying, hey, are they kind of close to a normal distribution? Now, with 10 per group, it's really hard to actually make that decision. Is it actually normally distributed? But in this case, Regina and I generated the data from a normal distribution. So we happen to know for sure that these are normally distributed data because ahead of time. So you have to make some judgment about whether the data are normally distributed or not. In terms of the spread of the data, we also know, because we generated the data, that the spread of the data is the same, but you can see that visually there's not a huge difference in the spread of the data. How spread out are those data? So it looks pretty good that we can say those assumptions are reasonably met. In this case, we'll show you an example soon when they're not met.
So that leads us to a t-test. And when we run the t-test, if you remember, we got the results. The difference between the means was 8 millimeters, negative 8 millimeters. And the p-value, if you remember, was 0.16. Okay, now let's go ahead and compare that to one more thing. Remember, I said t-test, ANOVA, linear regression were all the same thing. Let's focus on that linear regression. I'll go ahead and take this one. So,
sorry, I was just trying to see if I could redo my internet quickly.
Yeah, no, that's
because it
fine.
seems to be. Yeah.
You want to do that? You want to fiddle with that?
Yeah, I'm going to try to switch to the other computer to see if where it's wired
yeah.
now.
So I'll keep going on this. All right.
Yeah.
So linear regression, I don't know if you all remember from algebra class a very, very long time ago. You might have nightmares from your algebra class, but you learned how to find the equation for a straight line, linear, right? Straight line in there. And if you remember, there are 2 things that we need to find the equation for a straight line. And one of them is what we call the y-intercept. It's that bit. So what we want to do is find the best fitting line between these 2 groups of data, between the control group over here and the treatment group. And we want to find the best fitting line over here. The 2 things that we need for linear regression to be able to come up with the equation for this is, first of all, that intercept. Where does that line, that best fitting line, where does it hit that first group? It hits it at the mean, and that mean in the control group was 51 millimeters. That's the same thing that we found before when we were doing all of our descriptive statistics. The second thing that we look at is the slope, right? So we have to find a place to anchor the line, and then we want to see how steep that line is. Is it going up? Is it going down? Is it going straight? And the slope of the line, in statistics language, we call that the beta coefficient. It's simply, in this two-group test, the difference between the means of the two groups. And just as we showed before, that is -8 millimeters. So it's hitting the mean here and the mean here. So the slope of this line is -8 millimeters. Now, how do we take that information and come up with a regression equation? Regression equation looks a little scary, but is super powerful. And Kristin and I love teaching regression equations. So this is an example of a regression equation. You can often find this in the results section of a paper that you're reading. You might have to read a little deeper, but it's always worth it because it gives you more information. So let's go through what this means step by step. This first thing, tumor size, this is the thing, the dependent variable. This is the thing that we are interested in, we're measuring. So tumor size. We start with estimating tumor size. We start with an estimate of 51 millimeters. And that's just the mean over here. And then if a person is in the treatment group, we subtract 8 millimeters from that to go down to 43. But if they're in the control group, we're multiplying this by 0. And remember, when you multiply by 0, it makes all of this go away. So this is essentially saying if a person is in the control group, their estimated tumor size is simply 51 millimeters. If they're in the treatment group, their estimated tumor size is 51 minus 8 times 1, which is -8. And that is a very simple linear regression. And we use that then to find our results, just like we did with our t-statistic or t-test before. What we're doing here is testing that beta, that -8 millimeters. We find that we get a p-value of 0.16. Again, we're not doing this by hand. We're letting the computer do it, identical to the t-test. So I've not proven mathematically that they're the same. You can trust me on that, but you can satisfy yourself by taking the same data and running a t-test, running a regression, and saying, wait a minute, they come out to be the same thing. My students are amazed when they realize it's exactly the same. It's like you're finding the secret hidden things underneath. So why are we even talking about regression? So we gave a very simple example here. The nice thing about regression is it's a very flexible tool. You can use it for so many things, not just a t-test. A t-test is pretty narrow. You can only use it when you have two groups and you have this continuous difference that you're looking at. But a regression is very, very flexible. I don't do woodworking. I imagine maybe it would be like a very fancy, flexible kind of saw or screwdriver or something. It will let you, regression will let you look at multiple predictors at the same time. So instead of just looking at whether people are in their treatment group or the control group, we can look at, does age affect things? Does their body weight, their body mass, does that affect things? Just for what we call confounders, these other things that might influence the results. We can test for interactions, like maybe there's something about being elderly and obese that really changes what the effect of this experimental radiotherapy will provide. You can improve predictions. So maybe instead of a straight line, you want to make it a curved line. You can do all of this with regression. So it's much more flexible, but at its heart, it's the same thing. Now, Kristin, I wanted to give you just one little advanced equation so you can see how powerful linear regression can be. And is that, oh, are you back?
I'm trying from my phone.
Okay.
Hold on. I can't get the other computer to work either, so.
Okay.
So I don't know if this is any better.
So far, yes.
Okay, let's try from the phone then. Yep.
Okay. Do you want to take this, or you want me to take this one? You jump in next.
You can finish this and then I'll take the next one. Yeah.
All right. So remember, we had this regression equation, same thing we saw before. We're starting with tumor size. Remember, we were talking about this beta, right? Before this was negative 0.8 millimeters. Remember, we're multiplying it by 1 if you're in the treated group, or 0 if you're in the untreated group. So all of this is just the same as what we had before. But now we're adding in age, and we're adding in performance status score, you know, maybe how frail the patient is or how robust the patient is. And we're literally just adding in these extra predictors. So you create this wonderful, beautiful regression equation simply by adding in all of these things, and you can make it very, very complex. And in the end, you get this beta. It changes the beta once you account for all these other confounders. So now this is going to tell us about what the effect of treatment is on the tumor size if we account for the differences in age and performance status in the treated and untreated groups. So it lets us be a little bit more sophisticated on what we can make conclusions about.
All right, pop quiz number 2. So we've got a study that compared radiation dose received by patients in 2 clinical centers. So we've got 2 groups, Group A and Group B, and we've got our regression equation. The outcome variable is the radiation dose. And then we've got an intercept, which is 68. And we've got a value for our slope that goes with the treatment of 5. So the question is, what was the mean dose in Group B? Now, Group B has got a value of, if you're in Group B, you get a value of 1. If you're in Group A, you've got a value of 0. It's coded as a binary variable. So which of those is correct?
It's like a step function that you multiply.
Right.
Yes.
Very nice. Very nice. Yes. Exactly. In statistics, we call them dummy variables, which I find kind of adorable. So which was the mean dose in Group B, and which group had a higher mean dose, B or A?
Thank you for adapting the questions to radiation oncology.
We tried.
We did our best.
Yeah.
I had to look up what the radiation dose unit.
Yeah. Perfect.
Right? Okay.
Perfect.
Yeah.
And it's a good prescription, so you got it. Okay, let's wait for more people to answer. So far, it's going okay.
So the key to answering this is looking at this bit right here, multiplying by 1 if in Group B, 0 if in Group A.
All right, so we have 66% answering. I'm ending the poll and sharing results. So it's great to see that majority, 54% answered C.
Very nice.
Very nice. Yeah, so we're going to take the intercept, 68, plus 5 times 1. They get the 1 because they're in Group B. That's the indicator that they're in Group B. So 68 plus 5 is 73. Great job, everyone.
All right, now going back to our handy dandy chart in here, now we're going to be looking at alternatives. So far we've been saying, yes, it's fine. We got all of our assumptions of normality and spread. All of those were satisfied, but what if they are not satisfied? That is what we're going to be talking about now. We have different alternative tests. They're what we call non-parametric tests. And that just means they don't have the same parametric number-driven assumptions that you have when we're over here in this group.
So I'm going to go through a small made-up, this is hypothetical made-up example just to illustrate a case where you don't meet those assumptions. Again, the assumptions are we're looking for normality. The normality technically is of the residuals of the model, but that's often very close to that. My outcome variable is normally distributed. A little caveat there, if you have a big sample, it turns out it usually doesn't matter. So the normality assumption matters most when you have small samples, like 10 per group. The homogeneity of variances assumption, which is the spread of the data, that's a much nicer way to say it, Regina, that the spread of the data is sort of similar. That one matters only if the group sizes are unequal. So these assumptions even have caveats as to when they matter. But in this case, we've got a weight loss trial, and we have 10 dieters, 10 in group 1 and 10 in group 2. And let's say that in group 1, the people lost an average of 34.5 pounds, and in group 2, they lost an average of 18.5 pounds. So if you're a clinician looking at that, you might say, oh, well, I'm going to put all of my patients on diet 1 because clearly an average of 34.5 is better than 18.5. But we haven't yet looked at the underlying data.
So let's go back to our histogram. No, go ahead.
Yeah, no, you go ahead. Yeah.
All right, so let's go back to our histogram. Remember, we talked about this in our descriptive data last month, and we're just seeing the shape of this. Very nice. We can see that the mean is about 19 pounds, which is how many kilograms? We should have put this in kilograms, not 9 kilograms. Would that be about
something
right?
Like that? Yeah, something like that.
Okay. Around there. Okay. And the mean is about the same thing. So we can see that it's right around here. But what happened when we go to diet 1? Kristin, talk about diet 1.
Right. So, I mean, this is a made up hypothetical example, obviously, but you can see this happen. So I will point out, you can see what the problem is here is that there's somebody who lost 300 pounds. Now, the first thing I'm going to do as a data analyst is go to the people who collected the data and say, is this a mistake? Because you can imagine somebody putting an extra 0 or mistyping. But let's say we verified that this was actually correct. This is a highly left skewed variable with an distribution with an outlier because the median, which really reflects the entire group, is much smaller. They only lost 5 pounds as a median, even though the average is heavily weighed by that 300. So maybe we don't want to pay attention so much to the averages because it's so skewed by this one person.
So that leads us to what are our alternatives? And to just go through our list of questions again, you asked what is the outcome variable? We have weight change. It is continuous, yes. Are the observations correlated? No, because again, these are independent people. We have 2 groups, but here the assumptions of normality and equal spread are not met, specifically that one of normality, and we have a small n. So we are running into problems there, and that is why we are turning to what is called the Wilcoxon rank sum test, which also has an equivalent other test because Wilcoxon and Mann and Whitney, all of these old dead guys, all came up with the same idea at the same time, and they all named them different things. But Kristin and I like the name Wilcoxon rank sum test because it's very transparent about what it does and how it does it. And just to show you where it is on our chart, it's right there. And Kristin's going to go through what we actually do now.
Right. So we're going to actually just write out the data points because with 10 per group, you can write out the data. So in diet 1, if you look at the data kind of written out, it's very similar to what we saw in the histogram. You can see, well, you know, a lot of people didn't lose much weight at all. A few people did moderately well and 1 person did great. You want to compare that to diet 2. If you look at the numbers, you can see it's a really different picture than if you only look at the mean, right? Like everybody did pretty well, moderate or really well in diet 2. Nobody lost 300 pounds, but like overall, you might look at that and say, I think diet 2 is more reliable, right? So it's the rank sum tests. So it does what it says, and we're going to rank and we're going to sum.
So the ranks just means we are looking at all of these data points, you know, people who gained 4 pounds to people who lost 300 pounds in both groups. And then we're assigning them ranks, just meaning where are they? The rank 1 would be the person who lost the least, or in this case, gained the most. Someone gained 4 pounds, so they get a rank of 1. Then a weight gain of 3 pounds gets a rank of 2. And then 0, 3, 4, 5, 6. And then all of a sudden now we go to losing 11 pounds. We are 8 pounds, 10, 12, all of these. We're ranking all of these together from 1 to 20. So you can see the person with the greatest weight loss is over here at rank 20. And what this is doing is getting rid of the actual numbers. Now we're just looking at their position. So this person who lost 300 pounds was way, way down at the end. Remember, now we're bringing them in. Now they're 20. Now they're right next to the person who lost 30 pounds. So this is the crucial change that happens when you are looking at ranks and sums.
And it's a rank sum test. So guess what? We're going to sum the ranks. And of course, higher is better here. We want better ranks because the better you did, the higher the ranks. So we're then going to add up the ranks. So literally take within each group, add up the ranks, and you want to have a higher number here. And in diet 1, the sum of the ranks comes out to be 73. And then diet 2, if we add them up, we actually get a much higher number. We get 137. Now, we need a formal statistical test to tell us, does 73 differ from 137 statistically significant? Is that beyond what we'd expect just due to random variation? Yes. And that's what the Wilcoxon rank sum test does for us. And indeed, it does come out to be a significant p-value here.
Yes, very significant. But I want to point out that it is different than what you would think if you're just looking at the mean, right? We were looking at the mean weight difference, and the mean weight loss in diet 1 was hugely influenced by this one outlier person. So if you just look at the means, it looks like diet 1 is so much better. But this is where it's so important to check your assumptions and go underneath, because if we just went on that number, we would see this and actually get it wrong, because it's clear that once we look at the underlying data, we can see that diet 2 is consistently better, that this person is just an outlier.
The nice thing about these ranking tests is sometimes people ask, oh, I have an outlier, can I just dump them out of the data? And it's like, no, you don't get to just throw away data. But by that 300 was having a huge influence, but by making it a rank of 20, you're still counting them, but you're getting rid of that influence. That's the beauty of ranks.
Ready for pop quiz number 3. We have 4 situations again. Now, we've been talking about the Wilcoxon rank sum test. In which situation is that rank sum test most appropriate? And while you're reading the options, I will just read them out loud. Option A, where you're comparing the mean blood pressure between 2 independent groups and the data are normally distributed. Option B, we're looking at median pain scores between 2 independent groups, but the outcome is skewed. Skewed means it's not normal, it's not symmetric. Option C, we're comparing proportions of patients who improved in 2 independent groups. Or option D, we're comparing measurements taken before and after a treatment in a group of patients. So think about what Wilcoxon rank sum test, what that means and how that is different than a t-test, and when we might want to use that versus a t-test.
Okay, so we have 70% answering, and majority answered, well, it's close. 33% answered D, and B, 27% answered B, but correct is B.
Do you want to explain quickly, Kristin, why?
Sure, yeah. So The B is correct because we have two groups and the outcome is skewed, meaning it's not normally distributed. So that's when we would want to use our non-parametric, our ranking test like Wilcoxon rank sum. Because we're comparing a continuous outcome in two groups, the non-parametric test for that is that Wilcoxon rank sum test that we just went over. D is incorrect because it's a before and after case. So that's actually paired data, and you need a different test for paired data than even if those were non-parametric. If we wanted to analyze those measurements with a non-parametric test, it would be a different test. It's actually the Wilcoxon sign rank test, but it's a different one than the rank sum test. The rank sum is for two groups. Yeah.
All right, now we're going to talk about discrete outcomes. So that finished continuous outcomes. Again, continuous is when your outcome, your variable is a number, tumor size or weight loss or something like that. Now we're talking about discrete outcomes, which is actually the class that Kristin is teaching this quarter. That's
right. That's the one I had to duck out of early today. So discrete outcomes are things that are either binary, yes or no, or things that are categorical. And categorical meaning more than two categories. And the ones that we're going to talk about today, we're going to stick to the ones that are used when you have independent data, like independent different people. And there's a number of tests that we use. If you have a 2x2 table, meaning your exposure is binary and your outcome is binary, you can use what we call risk differences or relative risks. Some of you may have seen a chi-square before. That's for bigger tables. And the regression that you would use here for a binary outcome or a categorical outcome is called logistic regression. So let me set up this exercise in colon cancer randomized trial. This was a recent study. And again, we have an episode on it on the podcast because it was a pretty big deal. They did a randomized trial of giving people exercise after having had colon cancer. And that is a really hard study to do. In fact, this study took them 9 years to complete because it was hard to get, the right patients and get people to do exercise. And they were looking for fairly sedentary people, but they did find a survival benefit for exercise. So this was kind of a big deal. We all kind of think exercise after cancer is good, but there aren't a lot of actually hard data supporting that. So this is one of the few that's got really good randomized controlled trial data. So it was a randomized controlled trial. It was not blinded. The population was high-risk colon cancer survivors, and 445 of them got a structured exercise program. Again, not blinded. The control group got a health education only group where they were told to exercise but not given a specific program. The primary outcome was what we call recurrence, disease-free survival. So it was if you have death, recurrence, or a new primary cancer. It's called a composite outcome. Any one of those, it's combined to say yes or no, you had those or you didn't. So it's binary. You can treat the data from this trial as binary. Yes, you had one of those events or no, you didn't. We're going to see a little later that you can also incorporate time to say, not only did I have the event, but when did that event occur? And that matters in cancer, right? Because if your recurrence happens in 2 years versus in 10 years, that's very different. Right now, we're going to ignore time. So if we ignore time, it's just whether or not the event happened or not.
So again, the questions that we go through, what is the outcome variable? Now it's different, right? It's any event, yes or no. This makes it binary because we're not taking a measurement here. Are the observations correlated? No, because as Kristin pointed out, they are just two independent groups. Then we want to ask, is it a 2x2 table or an R by C table? Now, R by C just means it's not 2x2. That's a fancy statistical language for 2x2. What do we mean with 2x2? The first one is talking about how many categories are there, and we talked about there are two groups, right? You got the exercise intervention or just the regular health. So that's 2 right there for the predictor for the groups. And then we look at the outcome. Did you have any one of these events, yes or no, which is also 2 in there. So yes, it's a 2x2 table. Then we need to ask about the assumptions, just like we did with the t-test. Do we have sparse data? Means in those 2x2 tables, do we have any cells, any of those little squares where we're expecting to get fewer than 5 people, which means we have something with a very, very rare outcome. And we don't have this here at all. Like we expected to have a certain number of people getting cancer, not getting cancer in both groups.
And why is the number 5? Why is kind of?
Yeah. There's both a good mathematical reason and not a good mathematical reason. So that the answer is that the more you want it to be relatively balanced, when it gets too unbalanced, the model kind of fails, it falls apart. But the number of 5 is pretty arbitrary. So
Okay.
if it was 6, if it were 4, is it 7? We just have to cut it off somewhere, and we cut it off at 5.
Okay.
Okay, so here we're going to do what we saw on the chart, absolute risk difference or relative risk difference or both. And let me just show you where that is on the table. The chi-square test with this R by C, and that's if you are extending the 2 by 2 table in there. So we're going to do that first one, and Kristin's going to set this up now.
Yeah, so if we just look at how many events occurred in each group, it's a randomized trial, so that's pretty fair to just look at the counts because we have the same number in each group. They're followed for about the same amount of time. Like I said, later we're going to incorporate time, but for now we just said we started with 445. There were 93 events, that is a death, a cancer recurrence, or a new primary cancer in that exercise group versus 131 in the control group, which does seem somewhat different. And we can just calculate what we call the risk or the cumulative risk of developing any of these events. In the exercise group, it was 20.9%. So 93 divided by 445, it's about 21%. In the control group, it was bigger. It was 29%, almost 30%. So those look, reasonably different and meaningful in their difference.
But we want to go a little further and summarize this a little better. And there are 2 ways that we can summarize this. The first is the absolute difference in risks. And that is just what it sounds like, absolute difference, meaning we are taking those 2 risks, those percentages, the percent of people who have this outcome, and subtracting. So 20.9% minus 29.5%, the risk in the 2 groups is 8.6 percentage points. And remember, we talked about confidence intervals last time. We can say, or at the confidence interval, our best guess around for the true value for the absolute difference in the risk, 14.3 percentage points to 2.9 percentage points. Remember, that covers then, that does not cover 0. Sorry, we're looking at, did not cover 0. Forgot what I was doing. Did not cover 0. So our p-value is significant. It means that we are pretty sure that there is indeed a difference between those 2 groups. And we can take this 8.6 percentage point difference and put it into English words. So we have 8.6 fewer events per 100 people in the exercise group versus the control group. Now we can also look at risk ratio in here. So absolute difference is when we're subtracting the 2. Risk ratio is just what it sounds like. We're taking a ratio, we're dividing. So we're taking that risk in the first group and dividing it by the risk in the second group. So 20.9% divided by 29.5%, we get 0.71. Now here we want to look at the difference. We want to see, we want to compare it to 1. Because if it were 1, it would mean that the risks in the 2 groups were exactly the same. And here it's much smaller. And when we look at the confidence interval, that confidence interval does not cover 1. Our p-value is significant. It's much smaller than 0.05. And so we can take this 0.71 and turn it into words again to help with the interpretation. What we can do is compare this to 1. So 1 minus 0.71 is 0.29 or 29%. So we can say in the exercise group, they had a 29% reduction in events compared to those who were in the control group. So these are 2 different ways of summarizing the data that give us 2 very different stories. Do you have anything you want to add to that, Kristin?
Yeah, I mean, I personally love to see those absolute differences in risk, because then you know, like, how big.
Yeah.
Sometimes the risk ratio is just, it hides it, right? A 29% reduction in a very small risk is very different than a 29% reduction in a very big risk. So that's why it's often nice to have both, or just even, yeah, the absolute risk. Yeah.
Can you say relative reduction instead of just saying reduction? Because it can be confusing and interpreted as absolute reduction. That's
yeah, it's good to put the relative in. Yes, absolutely. Yep.
That's a great point. Yes.
I want to just talk briefly about logistic regression. The class I ducked out of early today, so like largely we talk about logistic regression. So there's a lot you can say about that, but I just want to point out that if, often that 2x2 table is just fine, especially for a randomized trial where you don't need to adjust for anything. But if you're doing something that's more observational, we often need to adjust for confounders. So we need a regression model. And the regression model, when we have a binary or categorical outcome, is logistic regression. It works a lot like linear regression, except we have to do something with the outcome variable because it's a yes-no variable, and so it doesn't model nicely to fit a line. So we make a little transformation of the outcome variable, and then we can do line fitting. It's very similar. The beta coefficients, though, end up translating into something called an odds ratio, which is similar to a risk ratio, but a little bit, it's the increase in odds rather than the relative increase in odds rather than risk. So same thing that Regina was explaining with linear regression. Let's say there was some reason, this was a randomized trial, so presumably age and BMI were balanced and we don't need to adjust for them. But let's say we were doing an observational study and people chose to be in the exercise group or the control group. Then we might need to adjust for things like age and BMI. So if we put those in the model, what we're saying is the beta for group, the slope for group, which again can be translated to an odds ratio, that is adjusted. That is the increase or decrease in the odds of the outcome, accounting for age and BMI. That's why it's powerful to use regression, because we can account for other variables. And again, you get odds ratios out. So that's why you see them so much in the literature, because logistic regression yields odds ratios. Lots of people use logistic regression. Therefore, there's a lot of odds ratios in the literature.
All right, now let's talk about test for survival outcomes. So this is very similar to what we were talking about with the discrete outcomes with this binary. Did they have an event, yes or no? Except now we are adding in one more thing. We're adding in time, the time to the event. And that is normally what we call survival outcomes. And these are the three that we will be talking about. This is where they have, this was at the very bottom of our list, time to event, for example, time to fracture. And we can talk about rate ratio, rate difference, Kaplan-Meier statistics, Cox regression.
So I'm going to use the exercise randomized trial again. I just want to point out that if we use time to event outcomes here, it is definitely more precise. We're going to get more precise measures. You'll see that the result looks very similar whether we use time to event or binary. And that's because in a randomized trial, we tend to be balanced in the amount of time and the total number of people followed. So often you'll see very similar results. It doesn't make a huge difference. But time to event in cancer is very important again, because it matters whether the recurrence happens immediately or whether it happens way down the road, or the death happens immediately or way down the road. So we like to take into account time. And in this randomized trial, they certainly measured time. So the main outcomes, the main results were presented in terms of time to event. So how do you look at time to event? Well, you need to know how long people were followed. So it turns out in the exercise trial, remember we said there were 93 events, death, recurrence, or new primaries in the exercise group. We need the denominator here is no longer just not the number of people, but it's the total number of person years. And a person year is every person, if a person is followed for 1 year, that's 1 person year. So this combines how many people I have and their average follow-up time. The average follow-up time here was about 5 years. So we had almost 500 people. They were followed for a little more than 5 years on average. So that gives us 2,500 person years. And it was very balanced. It was very close in the control group, because it tends to be with randomized trials. Remember, we had 131 events in the control group. So now we divide the number of events by the person years. And the reason this is nice is it gives us a rate. How quickly are events happening? And that's a little better than just saying the percent of people who are going to have an event. It tells us how many people are having an event each year. We like to translate these into whole numbers. So if we divide 93 by 2,500, we get a terrible decimal that we don't want to deal with. So we, instead of saying per person year, we say there are 3.7 events per 100 person year. So 100 people followed for a year. We would expect 3.7 on average, 3 to 4 of them to have an event in the exercise group. It was 5.4 in the control group, so definitely a little higher in the control group.
So here we're no longer just comparing risk. We're no longer just looking at this overall snapshot at the end of the study. We're looking at what Kristin is saying, the time to recurrence. And remember, time to recurrence, a new primary cancer or death. So we're going through our list of questions again. The type of variable is now time to event and not just binary. We have 2 independent groups. We have 2 groups. So we can use the rate ratio or rate difference. We can still do that. We can still ignore, using rates in here. So now instead of just having risk, now we can talk about the difference between the rates in here, or we can go even fancier and talk about Kaplan-Meier and Cox regression. And all of these are kind of known as survival analysis. And here's where we are seeing these on our chart.
So we can do the same thing that we did before, and we can talk about absolute differences in those rates if we want to compare the groups, or a ratio of those rates. So we're going to do the same thing. Again, the rate was 3.7 per 100 person years in the exercise group versus 5.4 in control. If I subtract those, it's negative 1.7. So 1.7 events fewer per 100 person years in the exercise group. This does turn out to be statistically significant. Notice the p-value is very similar to what we saw when we used the binary outcome. That's a trait of it being a randomized trial with very balanced groups. We can translate it into words. 1.7 fewer events are expected per 100 people in the exercise group versus the control group per year. So if we were following for 1 year, we'd expect about 2 fewer events in the exercise group versus the control group for every 100 people, about 1 or 2%. We can also divide, because people like to do ratio statistics. So we can divide the 3.7 divided by the 5.4. Notice we get very similar. The rate ratio is very similar to the risk ratio here. It's 0.69. Again, statistically significant. And it's in words, a 31% reduction in the rate of events, not the risk events, the rate of events in the exercise versus the control group. Again, these come out very similar to the risks here because this is a randomized trial. It could be very different if we were talking about a observational study where the groups were not balanced in follow-up time.
And again, this could be 31% relative reduction in the rate
Yes.
of events, like the value was said. Yes, very good. Okay, so Kaplan-Meier curve, some of you might have seen this. Some of you might have skipped over it if you're reading the literature. It's actually fun to look at, though, and it's very visual. So Kristin's going to go in a little bit more detail, but just notice this top one. This top line is talking about disease-free survival. Again, talking about continuing, with no death, no primary, new occurrence, no recurrence. Everyone's starting here at 100% because everyone's fine. And then they're dropping off bit by bit. And you want to look at the difference between these two, this top line, and this is over time. So we have months down here. And we have exercise group at the top and the control group, just a health education group at the bottom. And we want to see what is the difference between these two lines and how do we summarize that? So we can look at it visually and make an estimation, but we also need to find some way to summarize it numerically and do a statistical test on it.
So we're going to take a little brief detour here. This is something we do in the podcast, is to say, hey, let's stop for a minute and talk about a specific test outside the context of cancer. I just want to quickly go through, if you've seen a Kaplan-Meier curve before, what is it actually doing? What is it actually giving you so you have a little deeper understanding? So the key to the Kaplan-Meier methods is it's trying to estimate what is your probability of surviving past a certain time. And we do this all the time in oncology, right? We always talk about the 5-year survival rates, 10-year survival rates. It's very common in oncology. That it would be very easy to estimate that if we started with a certain number of people and then we saw, how many we had left at 5 years, how many we had left at 10 years. But that doesn't account for something called censoring, which we often see in studies. Censoring can occur because somebody dies of something that's, well, in this case, one of the outcomes is death. But if the outcome was just about cancer, they could be censored because something else happened to them. Or we just lose people to follow up because studies are complicated and people move and they decide not to continue in the study. We don't always have full data on everybody. So the key to the Kaplan-Meier, as I'm going to show you, is it accounts for that censoring. And you can get a p-value with the Kaplan-Meier test to say whether those curves are actually significantly different from one another. I'm going to go through a toy example just to illustrate how Kaplan-Meier works. So this is a made-up toy example, but let's say we just have 5 people and the outcome is death. Real simple. And let's say we're following people for a year, and the first thing that happens is that one of our subjects dies 4 months into the study. So that means at 4 months into the study, your survival probability is 80%. How did I get that? There were 5 people, and then we went down to 4. That's an 80% survival probability, so the curve drops down to 80%. But let's say that the next thing that happens is subject A drops out after 6 months. So they're censored. We don't know if they died or if they're alive for the last half of the year. But we do know that they were alive up to 6 months. We don't drop the curve there because we don't know that somebody died. There was no loss of survival, but we do stop following that person after, and that they're going to be accounted for in the denominator, as you'll see. And then let's say that at 7 months, subject C dies. We are going to drop the curve, but this is where it really gets. This is where it's the Kaplan-Meier methods are really important, because when we drop the curve, we say, how many people survived that second interval? Well, we only say there were 3 people in that second interval because we lost subject A along the way. So at the time, at 7 months, there were only 3 people in the denominator. There were 3 people at risk. So, and 2 of them survived. So the survival probability for that second interval from 4 to 7 months, we're going to say it's 2/3. And that's how we're accounting for the censoring. We're changing the denominator. We're not saying it's 2/4, we're saying it's 2/3. And then the total, let's say that, nothing else happens. B and D go to the whole end of the study. They're censored at the end of the study. So we just say nothing, the curve just, nothing happens to the curve. So how do we get the total probability of surviving a total of a year, the 1-year survival probability? We multiply the survival probability for each of those intervals. So the first interval is 4/5, the second interval is 2/3, and the last interval is actually 100%. So 4/5 times 2/3 times 1, that gives us a 1-year survival probability of 53%. And I think this is very intuitive because if you think about it carefully, right, we don't know what happened to subject A. So if you were kind of a glass half full person, you might say, well, the last time I saw subject A, they were alive. So I'm going to be glass half full and I'm going to say 3 out of 5 survived the year. That's being a little overly optimistic, but that would give you a 1-year survival estimate of 60%. Or you might be a kind of glass half empty person and you say, well, I don't know that subject A was alive at the end of the year, right? So I'm going to be glass half empty and say, well, I only saw 2 people alive at the end of the year. So it's going to be 2 out of 5. And I'm going to assume that subject A died sometime during that year. So you could be glass half empty and make it, and then your survival estimate would be 40%. If you were glass half full, you would say, hey, I'm going to make it 60%. Right. And so it's a compromise, right? It's a compromise. The censoring probability, the Kaplan-Meier estimate accounting for censoring is somewhere in between those. So it seems like a fair compromise. We're allowing that we're putting in some information that subject A survived part of the year, but we're not assuming they survived the whole year. That's the idea of a Kaplan-Meier.
I feel like we should have more things in life that are a compromise between half full and half empty.
Yes.
Just a great way to go. I feel like we're all at our extremes right now. The world is ending, or the world is.
That's true. Yes.
Yeah.
Very true.
Pop quiz number 4. This is asking a conceptual question. Why can we not usually just estimate survival over time by simply taking the number of people that did not have the event, the number of people that were, disease-free alive, and divided by the number of people who were in the study. Why can we not do that? This is getting to the heart of why do we have this particular thing that we just talked about? Is the problem because the outcomes are rare? A. Is it B, because the outcomes may be unbalanced at baseline? Because C, follow-up time differs and censoring occurs. And just a reminder that censoring means we lose that person to follow up. Maybe they move away or they stop participating in the study for some reason. That's the censoring. Or D, because hazards and survival are not constant. One way to think about answering this question is to think about the example that Kristin just went through. What was the problem that we were addressing with this Kaplan-Meier in here? What was the thing that we said when she was giving all the hypothetical examples of person A through E? What was the thing that happened in there that threw a little wrench into the works that made a problem?
Okay, we have a 72% answering, so I'm ending the poll and sharing result. And majority answered C, 54%.
Good job. Everyone's paying attention. So
Thank
late
you.
in the game,
Yes.
actually. Right. Kristin, you want to walk through this?
Yeah, so, reading a Kaplan-Meier curve, every point on that curve represents the survival probability at that time, but we don't usually talk about the entire curve. In cancer, we often like to take certain benchmarks, like what was the 5-year survival. So in this paper, they reported the 5-year disease-free survival. So what is your chances of making it 5 years without recurrence, new primary, or death? And it was 80%. We're just reading that off the Kaplan-Meier curve. That 80.3% is exactly where we are on that curve, on that orange curve at 5 years, versus 73.9% in the control group at 5 years. So this is just another way to present the data, which we often do in oncology. It comes out of a Kaplan-Meier estimate.
I like the Kaplan-Meier curve, though, because as we've talked about, this is a little arbitrary. 5 years, okay. What about 5 years and 1 month, or 6 years? So you can see what is happening over time, and you can see how this split, this difference between the two groups, widens throughout the study.
I also like how you can see on this, though, that Regina, by 10 years, there aren't many people left in the study because most people were not followed that long. Yeah. So you can see the numbers at the bottom, and that's important to pay attention to, that the confidence intervals there would be wide.
Yeah. Yes, good point. So it's visual here, but then you can go down here and get a little bit more granular and get something in here. By the end of it, not many people left at all. What do we want to talk about here, Kristin?
So often the Kaplan-Meier curve, because it's a curve, you can calculate something like a 5-year survival probability, but then we often you'll almost always see a Kaplan-Meier curve paired with a Cox regression. So remember, Cox regression is just the regression. We've been talking about regression techniques. It's the proper regression technique for a time to event outcome. We often like to use regression because we might want to adjust for something like clinical site, or just to get a nice number. Cox regression gives us something called a hazard ratio, which you can only get out of a Cox regression. Hazard ratio is very similar to a rate ratio. It's basically the same thing, except it's an instantaneous rate ratio. So it's talking about, over time rather than a rate ratio being kind of an average over time. So it's very similar, though, to a rate ratio. It comes out to be 0.72 here, yeah.
Just to put this into perspective, we've been talking about regression in each of these situations, right? And regression is the very flexible tool. We talked about linear regression, and we said the thing that was important there was the slope between the two. We talked about logistic regression, and we talked about odds ratio is the little thing that you get out here. So this is the same thing. The hazard ratio is kind of giving us like the difference between the two groups, the slopes of the two groups. So it's the same idea in all of these. We're just dressing it up in fancier and fancier clothing. And it comes out very similar. It's 0.72. Remember, the rate ratio here was 0.69.
So it turns out that whether you use the fancy regression or the kind of hand paper method, you're getting very similar results in this case.
So it looks like exercise group significantly improves this disease-free survival.
Yeah.
Yes, very impressive, and a large effect, which is amazing when you consider that it's just exercise.
Yeah.
That is wonderful.
Although just exercise sometimes that, getting people to do it.
Do it.
Right.
Yes. In this randomized trial, they had a trainer. They had free access to gyms. I would love to have access to a trainer that would come wake me up every day. Yes. Make me exercise. So here's what I was talking about just a moment ago. We have these different types of regression. Linear regression, talking about the slope, and it's telling you how much the outcome variable is changing for every change in the predictor. Odd ratio is telling you how much the odds of the outcome is changing per every 1 unit increase in the predictor. Hazard ratio for Cox regression is telling you about the rate of the outcome. So we're starting with just a simple outcome, then we're talking about odds of the outcome, now we're talking about the rate of the outcome, but still that same idea underneath.
Regina, we didn't have enough time to talk about odds ratios in this lecture just because it was already jam-packed, but we do talk about odds ratios. I think it was in the Batman episode of our podcast. If anybody wants the longer explanation of odds ratios and how to interpret them and how they can go wrong, that's a great topic. We just didn't have time to fit it in here. So Batman.
Batman, it's very fun. They wanted to see whether the presence of a superhero, Batman, would make people be nicer on the metro, on the underground system. Yep. So check that one out. That one's good. All right, last pop quiz.
So in this one, there's a randomized trial and participants were followed for varying lengths of time, and investigators plan to present the results using a Cox regression model. So what of the effect measures that we've talked about today is most comparable to the output of the Cox model, which again is that hazard ratio? Which one is the most similar to the hazard ratio we've just seen today?
Listen to the words Kristin just said.
Yes.
Hazard ratio.
Yes.
And remember the difference between risk and rate. What is the difference between risk and rate? Risk was what we talked about earlier when we said we're going to ignore the time to event, and rate is like it's like speed, how fast you're driving a car. It's taking into account time. You can tell I want people to do well in the pop quiz. I don't know why. I just have this. I want to help people.
You're very helpful. Okay, so 52% participated, so 58. And in the poll sharing result, 50% answered B, risk ratio.
Yeah. Kristin, you want to talk about?
Yeah, I mean, in this case, the risk ratio, the rate ratio, and the hazard ratio all look very similar. But remember, the Cox model gives you a hazard ratio, which is talking about rates. So the most similar is the rate ratio. The rate ratio incorporates time. Our Cox regression model, just like the Kaplan-Meier, also incorporates time. That risk ratio, remember, it was just how many people had the event out of the total. It didn't incorporate time. That's all.
A little bit confusing, I think, to get that.
Yes.
Mm-hmm.
This one was a hard one. This was a hard one.
We did talk about this one in the exercise and cancer episode of Normal Curves. So if you want to understand all these different measures, we did go into those in a little bit more detail in that one. Yes.
We had some good analogies in that one as well.
We have being voted off the island, I think, was the analogy. You may not know that reference though, Regina.
I know. We used reality show competition.
Oh, I see.
So just want to point out, we have crammed a lot into this lecture. We want to kind of go for breadth rather than depth here. Regina and I have lots of other resources. So we've talked a lot about the podcast, which if you want a fun way to learn, we're going to some depth into some of the statistics, but we're really fun examples. And we try to use a lot of analogies that you can remember. We also have some online courses on demystifying data is an intro stats course. So if you really want to start at the intuitive level, you see how Regina makes everything really fun and easy to understand. We co-teach that one, and it really gives you a great introduction to and friendly, non-scary introduction to statistics. I have a medical statistics program, which gets in a little bit more depth, and we get a little bit underneath the hood, and you can learn some programming. And then Regina and I have a clinical trials course that we do together if you want to learn how clinical trials work. Yeah.
That's awesome. Thank you so much. This was really incredible. And thank you for laying down all the basics and details for the regression models. That was very interesting. And I wish I had this lecture when I started my research in clinical trials. So that's quite incredible. Thank you so much. So I'd like to open the floor for questions. If anyone has questions, please you can turn on your microphones, cameras, if you'd like to ask the question. Maybe I'll just start with something. What is the most common kind of a misunderstood statistical analysis and interpretation of variables? What do you see in the publications, let's say? But you critique the papers, right? But what? Yeah, we talked about p-values, but in along these lines in this topic.
Logistic regression, maybe? What would you say, Kristin? Logistic regression?
Most common error?
Right.
Yeah. Yeah, I mean, there's so many things. So Regina and I critique a lot of papers, and some things are very, very basic. It doesn't even get to the level of did you pick the correct statistical model or did you interpret it? A lot of what Regina and I pick up in papers is like the numbers don't make sense, right? So there's some very basic mistakes that can be avoided by good data cleaning, good data management, making sure you have a final data set, you know everything has been cleaned and checked, and you're not running around with 3 different data sets, which I think often happens with papers. So there's the basic stuff, but for something like logistic regression, there's some different things that could go wrong. Commonly with logistic regression, I'd say the 2 most common problems I see there, sometimes with logistic regression, you don't realize you have sparse numbers. So when you're doing categorical data analysis, sometimes you're dividing things into smaller and smaller categories. So your outcome might be binary, yes or no. And then maybe you have predictors, you're in this group or not, and then you're in this age group or not. And underneath the hood, you may not realize that you start having really small numbers in some of the groups. That can cause your model to give you really weird results. I saw one of the papers we're looking at for season 2 of the podcast I was looking at yesterday. This is hysterical. They reported odds ratios of infinity in their paper.
Wow.
So never do that. I've never seen that before. They literally took the infinity out. The computer said infinity, they put in them all. That's a sign that you have underlying sparse data. You don't want to put infinity in your paper. You want to say, hey, I want to understand why I have sparse data, and maybe I'm not going to be able to even give an effect measure like an odds ratio for that data. So that's one error I commonly see. It's sparse data that's kind of hidden and people don't realize it. The second one is the interpretation of odds ratios, particularly from if you have studies that are not a case control study. So case control study odds ratios often are very similar to risk ratios, and we can interpret them as such because case control studies typically have rare diseases. But if you're doing a cross-sectional or a cohort study and you present odds ratios, just be aware that those odds ratios may look very big. You might have an odds ratio of 5, and you might think, oh, I have a 5-fold increase in the likelihood of a bad event happening. But it's actually a 5-fold increase in odds, and the increase in likelihood might be very small to the increase in odds. So it might be a 20% increase in your risk, but the odds ratio is 5, and people often misinterpret those odds ratios as ratios. Yeah. So be very careful in odds ratios when your outcome is common.
I see.
Yeah, I'll just add in that it's very important to really think about what your variables are what they represent and how they're measured. Sometimes, I know, Natalia, you had sent us a question about the types of variables that people were measuring on hospitals, right? And staffing. So are you measuring staffing in numbers, in percentages? Is it like an ordinal scale, 1, 2, or 3? Is it positive change, negative change, or no change? Is it 0 or 1? How are all of these things measured? And that was the very beginning of what we talked about. And sometimes if you're just getting your data in a spreadsheet, you say 0, 1, well, they're numbers, and then they go ahead. And I've seen people try to figure out whether a 0, 1 number is normally distributed or not. And there's no number. If it's yes or no, there's no normal distribution there. So I think it's really important to sit down and think about what your actual variable is.
And I also have a question, like, for example, let's say if people rank the satisfaction, it's 1 to 10, right? And then you present it as average plus minus standard deviation, but then it goes over 10, right? What's your opinion on this and how to deal with this?
It's not ideal. We use that sort of satisfaction number.
So still okay to present it that way?
Usually what's better is when, it's okay as long as you're making it very clear what your scale is, 1 to 10. I would propose reporting median instead of mean in there. Reporting quartiles.
Quartiles, yeah, that's what we did at the end.
Okay, good, yes. Yes, and also reporting what the most frequent outcome is. Sometimes that can be very helpful. Yeah.
I see. Okay, thank you. Thank you so much. That was an excellent lecture, and I hope Ukrainian colleagues learned a lot from this, and then that would help them to evaluate research papers and also write their own research clinical protocols. So multiple people are working on clinical protocols right now, so that would be very, very useful skill for them. Thank you. I appreciate all your help, and we'll continue listening to your podcast. So looking forward to new episodes.
Thank you, Natalia.
Yeah, thank you both.
Thanks, everyone.
Thanks, everyone.
Yes. Bye, everyone.
Bye.